You have learned how to draw Lewis dot diagrams for atoms. Now let's use that skill to help you draw representations of molecules. This will help you understand both the inner workings of the molecule and the intermolecular attractions. And I'm indebted to Dr. Harding at UCLA for these simple rules, which have been passed down to us. And we'll also be able to draw polyatomic covalently bonded ions. Remember, a polyatomic ion is itself held together by covalent bonds. Let's talk about neutral molecules first. For example, carbon dioxide. Of course, the first thing you need to do is draw the Lewis structure for the valence electrons, remember valence electrons only, of the atoms involved in the molecule. Here we have carbon on the left, which has 4 valence electrons, and oxygen on the right, which has 6. Now, if there's more than one atom type in the molecule, you're going to put the most metallic or least electronegative in the center. That's going to be your central atom. And remember, of course, that the most electronegative elements are to the upper right of the periodic table. And as you go more to the left, they become less electronegative. And as you go to more down, they become less electronegative. So, we're going to put the carbon in the middle and the oxygen on either wing. Then we arrange the electrons so that each atom contributes 1 electron to a single bond between each atom. So the oxygen needs to bond to the carbon here, and the second oxygen needs to bond to the carbon here. Now make sure you maintain the total number of electrons that you had to begin with as you do this. As you can see, there is a single bond here, but we have unpaired, unbonded electrons on that oxygen and on this carbon. So both oxygens and the carbon have unbonded electrons. Are the octets complete? Well, no. This oxygen has 7, this carbon still now has 6, and this oxygen has 7. If we had complete octets, we would have a complete Lewis dot structure, but we do not here. If the octets are incomplete and more electrons remain to be shared, we will move 1 electron per bond per atom to make another bond. And so that's what we've done here. We've taken the extra electron here and here and put it between the carbon and oxygen. And we've taken the extra electron here and here and put it between the carbon and oxygen here, making double bonds. Now in some structures, as for instance in the boron of boron trifluoride, you'll have an open octet. And sometimes you have 10 electrons, as in sulfur pentafluoride. Now you repeat steps 4 and 5 as needed until you have a complete octet around everything. Then you're going to move the unshared pairs, as in Vesiper theory, so that any repulsive effects are considered. This gets the molecule to be at minimum energy, and that's what we're going to do now. As you can see, we've moved those unpaired, unshared electrons over to the other side of the molecule. And we have the shared electrons, the double bonds, in between the atoms of the molecule. This molecule must be linear because this double bond and this double bond will repel each other, and 180 degrees would have the minimum energy. Okay, your turn. Draw the electron configuration for ethane, C2H6. The carbons are, of course, in the central position because they are the more electronegative. The carbons must be bonded to each other or the molecule would fall apart. Here's the solution to that problem. Now, you must remember, of course, we have flattened out what is a three-dimensional molecule. You may recall that carbon, when it's bonded 4 times, has a tetrahedral configuration. So you can think, for instance, in terms if the carbons are in the plane, then these hydrogens might be out of the plane, kind of towards us, and this hydrogen would be back behind the plane. IUPAC and AP folks prefer you to show bonded electron pairs as lines. So instead of what we saw in the previous slide, the electron pair, we will show a clear bond with lines. Now, if you have a negatively charged ion like the carbonate, you're going to use the same procedure, and then as the last step, you're going to add 1 electron per negative charge to fill up any octets that may not be filled. So here is the carbonate ion, and as you can see, we've added electrons here, and of course negative charge on the 2 sides. This completes the work with a negative 2 charge. We have a single bond here and here, and a double bond here. What do you think the shape of this would be? Well, you've got 1, 2, 3 centers, and they're going to repel each other, so that you will get here a planar shape with something close to 120-degree bond angles. So this is the carbonate ion. Remember, the last thing we did was add the 2 negative charge in the form of 2 electrons. IUPAC and AP will expect you to show the bonded pairs as lines. Now it's your turn. Draw a Lewis structure for the cyanide ion, Cn-, using the rules that we've taught you. Here are actually 3 solutions. The triple bond here with a negative charge over here, a double bond with a negative charge on the nitrogen, and then a really special one here with charges separated. Now, these we treat as resonant structures. Each can have some validity, and we'd have to do spectroscopic studies to see if any one of them predominates. For instance, if we found a very short bond here because of a triple bond, if we found that that was predominant, then we would perhaps say that this is the most likely of them to occur. For positively charged ions, we use exactly the same procedure, but then we're going to remove an electron probably before we start forming bonds. We remove 1 electron for each positive charge so that we avoid expanded octets. When we use this procedure for positively charged ions, it may be necessary to have some atoms with expanded octets. For instance, here, nitrogen will have an expanded octet. For each unit of positive charge on the ion, you're going to remove an electron from the expanded octet. If you do this correctly, the final structure will have no first or second period elements with expanded octets. Why do you want that? Well, think about it. There are 3d electron orbitals, but there's no d orbitals on the first or second energy levels. So here is the ammonium ion before we remove the electron, and since ammonium ion has a 1+ charge, we remove that 9th electron and add the plus here. So we have taken the NH4 and made it NH4+. It's fortunate that this is the only polyatomic cation that we frequently draw, because we don't have to do this very much.